Well, here we have a differential equation with initial conditions on y and y prime. The y prime is a little smudged, so I'll fix that. But we transform this equation. How do you transform the equation? Well, we have to transform y and its derivatives. Okay, so we do the Laplace transform. It's a linear operator. We can apply it. If we apply it to a linear combination of functions on the left, we get the linear combination of the corresponding Laplace transforms. Everything being linear, we get the Laplace transform of y double prime. We get the Laplace transform of 2y prime, which is just 2 times the Laplace transform of y prime, because the Laplace transform is so nicely linear. We have a plus there. And then, again, due to all the linearity, the Laplace transform of the 4y is 4 Laplace transform of y. We have a plus this, so we have a plus here. So there we have it. We've transformed it. Well, we're going to have to write a few things out, but that's okay. And then we have to do the Laplace transform of the sine of pi t. Now we already see that this is the Laplace transform of the sine of omega t, so we know what that's going to be. It's going to be easy. What about all these derivatives? Well, we've just been through that a little more than maybe we should have. And I think I just managed to, I wrote it down right. Looks like I wrote it down wrong and then corrected it. That's fairly typical. Would have been better to write this as minus sy of 0 and decreasing powers of s. Less confusing, and if you're just trying to remember it rather than rederive it in your head, which in my case would be a much better idea these days, you have that. Okay. This is the Laplace transform of y double prime. Okay, just go back to the formula for the Laplace transform of f double prime. It's not f anymore, it's y, but it's just a function of t, so there it is. And the Laplace transform of y prime is s L of y minus y of 0. Okay, and you have 2 times that. And the Laplace transform of y, of course, is the Laplace transform of y. And the Laplace transform of the sine of pi t, it's omega over s squared plus omega squared. Omega is equal to pi, so it's pi over s squared plus pi squared. Now, how is that helpful? Well, it's helpful because the only thing that we don't know, well, of course, s is unknown, but we're never going to actually solve for s. Remember, we inverse transform expressions that involve s, right? So we don't have to solve for s. The one thing we don't know is L of y. If we know the Laplace transform of y, then hopefully we can inverse transform it. We can find the function whose transform is equal to that. Well, this is nothing but a linear equation in L, if we regard s as just a constant that goes along for the moment. Okay? So we just solve this for L. Now, we also, well, actually I went ahead and wrote it out. I wrote all the factors of L in one set of parentheses, s squared, 2s, and 4. That was easy. And then we have our minus y prime of 0 there, and minus s y of 0, and minus 2y of 0, because remember that this y of 0 has a factor of 2 out in front because of the 2 that we had here and here. Okay? So there it is. I just wrote it out carefully, and now we'll try to sort it out. And of course, on the right-hand side, we have the Laplace transform, the sine of pi t. I didn't all that explicitly do these substitutions. But y prime of 0 is negative 5, so minus y prime of 0 is going to be plus 5. So I just kind of wrote these numbers down just to keep track of where they were so that I could then write a simplification. And sy of 0, well, that's s times 3, so that's 3s, and it's minus, so you have a negative 3s. And then you got minus 2y of 0. Well, y of 0 is 3, so 2y of 0 is 6, so negative 2y of 0 is negative 6. So all this stuff here is just negative 5 minus 6 minus 3s, and that's just negative 1 minus 3s. So all this then becomes on this side. Now we're trying to solve for L of y, so first thing we're going to do is going to add 1 plus 3s to both sides. So we get pi over s squared plus pi squared plus 1 plus 3s. And that'll be equal to this multiple of the Laplace transform. To solve for the Laplace transform, we just divide by that multiple. So we get this mess, okay? But remembering what we did, and I don't have the expression up here, yeah I do, with s plus 1 over s squared plus pi squared over 4, just kind of follow our lead, you know, we did s over this plus 1 over this, and we were able to inverse transform s over this and 1 over this. Well, we're going to do the same thing here and hope that we can inverse transform the expressions that we end up with. So what do we have? Well, we have pi over s squared plus pi squared, and then of course we're dividing by this. That's going to give us pi over s squared plus pi squared times this thing we're dividing by, also in the denominator. Okay? And then we're going to have 1 over this, 1 over s squared plus 2s plus 4, this thing, and 3s over this, 3s over s squared plus 2s plus 4. Now we try to inverse transform all this stuff. And that gets a little hairy. It's not too bad over here, because what we're going to end up doing is completing the square. You notice I know to complete the square. We have to know how to complete the square. Okay? And do a partial fraction on this one, because we have two polynomials here. And these are also irreducible polynomials, which is how we know we want to complete the square here. If this was factorable, we'd factor it into two linear factors, and we'd just do partial fractions. Now, if you're as rusty as I'm afraid you are, even though I've been warning you about partial fractions for some time, but I know students, I was one once, and I was the same way. Okay, at the very last minute you're going to learn partial fractions, or maybe not, but I hope you will. And I told you need to do this before our next class. Okay, so hopefully you made a note, and when we come back for our next class, which is in the morning before I'll be able to get these posted, you'll recall how to do these things so that when I do them, you'll be with me. Okay, well, I sincerely hope that's the case. So that's really where we're going to start our next class. We're going to see how to deal with all this stuff. We're just going to dive right into it and see how it works out.